Namaste everyone. Welcome to current electricity classes. We have finished meter bridge. Now we have to move on to the potentiometer. First of all, we will have a little bit of theory of potentiometer. How does it work and on what basis, on what principle it is working and what is the thing involved in it. Then we will move on to the problems. So as I told in the previous class, out of meter bridge and out of potentiometer, you can definitely expect one question for NEET exam. And these questions are always in a standard of in such that you can solve it easily. So there will not be any much problem in solving it. Okay, what is a potentiometer? Instrument used to measure the potential difference, right? Or EMF of a cell especially. And the speciality of the potentiometer is it doesn't draw any current from the circuit to which it is connected. Suppose you connect a voltmeter, whatever be the quality of the voltmeter, it draws some current. Whereas potentiometer doesn't disturb the battery and it measures the EMF. And what does it contain? It is very simple. I will go on narrating it like this. This theory is helpful to you in understanding the problems. Now suppose you have a battery, say 10 volt battery. I will use very convenient values so that it becomes easier, because tensor table is very easy and you will remember all those things. So that's why I used 10 volt. So this is a fixed battery, 10 volt battery. Sir, will I get 5 volt out of it? No, very difficult. It's not a variable battery. You can't change the value. Can you get 8 volt? No. But you can do one thing. How do I get 10 volt, 8 volt, 6 volt, 5 volt, 3 volt from a fixed 10 volt battery? Very easy. You take the 10 volt battery and connect it to a uniform wire of certain resistance R. Okay. These wires don't have any resistance. You connect it to a uniform wire of resistance R, like this. Okay. So this is connected to this. These wires don't have resistance. Let the resistance of this be 10 ohm and let it be of 10 meter. Again, I say I used all 10, 10, 10 because you know the division of 10. You are very good in tensor table. So 10 meter, 10 ohm, 10 volt battery. Sir, where do I get 8 volt? Where do I get 6 volt? Where do I get 3.33 volt? It's very simple. This 10 ohm wire, it's a uniform wire like this, like its cross-sectional area is same everywhere. It's uniform wire. So if you cut, and you know that R is directly proportional to length, R equal to rho L by A. If you cut this wire exactly at the center, you know that it is exactly 5 ohm, 5 ohm. Divide this 10 ohm resistor into 5 parts, 2 ohm, 2 ohm, 2 ohm, 2 ohm. It should be divided into equal parts. So I can assume that this wire is made up of many resistors, small resistors connected in series. 5 2 ohm resistance connected in series, or 10 1 ohm resistances connected in series. So why can't I take it like that? And if it is so, what happens is, if I can write an equivalent circuit like this, suppose there are 5 2 ohm resistances like this, 1 2 3 4 5. Okay, enough. This is 2 ohm, 2 ohm, 2 ohm, 2 ohm, 2 ohm. 5 2 ohm resistances are connected in series. So I divide it into 5 parts, then connect the 10 volt battery. Now what has happened? What is the current through this? I equal to E by R plus R, no internal resistance. Then this is V by R, 10 ohm, this is 1 ampere. 1 ampere is the current, and in series current is same in all the resistors, you know it. When 1 ampere flows through 2 ohm, what is the voltage here? It is say 2 volt, and it is 2 volt, 2 volt, 2 volt, 2 volt, everywhere you get 2 volt. Now how much voltage you want? Sir, I want 4 volt. Take a voltmeter, connect it here. Don't you get 2 volt here from here to here? Sir, I want 8 volt. Connect a voltmeter here and here. 2 plus 2 plus 2 plus 2. You will get 8 volt. So you will get every voltage. Sir, I want to get 3 volt. Where should I connect? That becomes a problem. But in this wire, you don't have any such problem, because in a uniform wire, resistance is distributed uniformly. If you want 5 ohm resistance, cut it at the middle, you will get 5 ohm. If you want 3 ohm resistance, cut it at the 3 meter, because 10 meter possesses 10 ohm. How much length possesses 3 ohm? 3 meter. So select 3 meter, you will get 3 ohm. I want 2.5 ohm, sir, 2.5 meter. So according to the length, you will get resistance. That means if 10 volt is connected to a 10 meter 10 ohm wire, and if I take a voltmeter, this 10 volt is distributed everywhere. That is why it is called potential divider. Potentiometer means in a certain meter length of the wire, potential is divided. You will get any voltage that you want within 10 volt, but within 10 volt, not more than 10 volt, because the supply itself is 10 volt. Sir, I want 7.3 volt. Connect the positive of the voltmeter here. Take the negative of the voltmeter to 7.3 meters, so that this is 7.3 meter. Definitely 7.3 meter will have 7.3 ohm. 7.3 ohm into current 1 ampere, 7.3 volt. So whatever the voltage you want, sir, I want 2.22 volt. Connect it at 2.22 meters. So you are able to get all the voltages within 10 volt. That is the potential divider. Okay, now what is the beauty of potentiometer now? This is 10 volt, say, okay, right. And we have, suppose I want to, what is the application of a potentiometer? Potentiometer is used to find out the EMF of a cell, or compare the EMF of two cells, or it is used to find out the internal resistance of a cell. That is also possible. Okay, sir, how to find out the EMF of a cell? I will go to a very theoretical and very ideal case. Take a battery, connect it to a galvanometer, very good galvanometer with very less resistance, and so this is the EMF I want to find it out. With a jockey, keep it on moving across the wire, a connector. Okay, now you move this jockey over this wire till you get galvanometer deflection 0. Your aim is to find out the value of EMF of this secondary cell. Okay, this is primary cell. Primary cell is the one which gives energy to the wire, potentiometer wire. Secondary cell is the one which is experimental cell, of which EMF is to be found out, or internal resistance has to be found out. Okay, you have connected the battery here, and there is a balancing length here. Say the balancing length is some 3.5 meters. I conclude, what do you mean by balancing length 3.5 meter? I get the galvanometer deflection 0. Okay, till that I will move it. That is 3.5 meter. I conclude that EMF of this cell is 3.5 volt. This is most ideal case I am explaining, just to understand the theory behind it. Sir, why it is 3.5 volt? It is very simple. This 3.5 meter wire should drop out of 10 volt 3.5 volt, because we get a potential gradient, right? The potential drop per unit length. So we have a term called potential drop per unit length. Per unit length. What do you mean by that, sir? For each 1 meter, how much voltage you get? Over a length of 10 meter, I have 10 volt. Over a length of 1 meter, how much I have? 1 volt per meter. Am I right? This is very easy number. For each 1 meter, I have 1 volt, and for 10 meters, I have 10 volt. What about then 3.5 meter? So if 1 volt per meter is the potential drop, what is for 3.33 meters? Because for 1 meter, this is in the denominator, to the power minus 1, right? 1 volt per meter. For 1 meter, I get 1 volt. What about 3.33 meters? That is 3.33 volt. Okay, you get 3.5, isn't it? Our number is 3.5. Let it be 3.5, 3.5, this is 3.5, right? For 1 meter, I get 1 volt. That is called potential drop per unit length, potential per unit length. So whatever the phi value you get, voltage drop per unit length. If you have what is the value of 1 kg of tomato, you can get the value of any kgs of tomato. Multiply that. I have purchased 5 kgs, 5 into the value for 1 kg. If you have 1 meter voltage drop, multiply to any length, you will get the voltage. Sir, this is 3.5 volt, I agree. Why this is 3.5? What is the reason for saying that this is also 3.5? That experimental cell is also of EMF 3.5 volt? Very simple. I can write the equivalent circuit for this one. Now you ask this battery, secondary cell, experimental cell, how are you? Sir, I am fine. Where are you connected now? Sir, I have been connected along with the galvanometer across a wire which has a potential drop. So what is that wire? Sir, that wire appears like a battery for me. Cell will say, this wire appears like a battery for me. How much voltage battery? 3.5 volt. So shall I draw an equivalent circuit for this one? Yes. Battery says, sir, I am of EMF E. I have a galvanometer of 0 resistance with me, and myself and galvanometer are connected across a cell of EMF 3.5 volt. This part of the wire is taken as 3.5 volt. Now, what is the condition of the galvanometer? This part of the wire, which is acting like a 3.5 volt, will try to send the current like this through the galvanometer, but this cell already present will try to send the current like this in the galvanometer. So one current like this in the galvanometer, another current like this in the galvanometer. Galvanometer is in a confusion now, whether to go to the other side and to the left side. Galvanometer will go to the side along which current is more, isn't it? If one direction current is stronger than the other one, definitely galvanometer will go to that side. But galvanometer doesn't show any deflection. That's why we called it this as a point of balancing point. It will never show the direction because this current and this current are equal in magnitude, opposite in direction. Net current is 0. And that net current is 0 possible only when this one and this one are identical. That's why I say EMF of this cell is 3.5 volt. So when you have two identical cells connected in the opposite direction, nothing flows in the circuit. So because they will try to send the current in opposite direction, and those two currents, moreover, they are equal, they cancel each other. That is the beauty of this. So this is most ideal case. Of course, there may be internal resistance here and some other factors coming into picture. When they come into picture, we will analyze it, what to do. Okay, sir, now if I connect a 6 volt battery here, will it get balanced, sir? Definitely. Keep on moving this. Sir, now if you place it here, this galvanometer doesn't show 0 deflection, because what this 3 volt or 3.5 volt battery, acting battery here, will send the current like this, will be weaker, and the current sent by the 6 volt battery will be stronger, so there will be deflection. So where you have to search the balancing point now? You have to go on searching it in up to 6 meters, so that when you reach 6 meters, you will get 6 volt here, and this battery will have 6 volt. Again, the current will be 0. So according to the EMF of this cell, there will be a balancing line, which will give the equivalent EMF and cancel the currents, and the galvanometer current will be 0. So you can find out the EMF of this cell. That is possible, one thing. And sir, if I don't know what is the EMF of primary cell, if I don't know what are the potential drops here, can I find out the EMF of the unknown cell? Possible. How? I'll rub this. Even if you don't know what is the EMF of the primary cell, say this is primary cell. Primary cell is a part of a circuit. It energizes divides the potential on the wire, and it has nothing to do with the experimental cell. It energizes the whole circuit. Okay. Sir, if I don't know what is the EMF of this, can I find out what is the EMF of this cell? Yes, comparison method. That is what you did in the laboratory this year. Now, I rub this. So what I'll do is, I don't know how much voltage drop is occurring in each part of the wire, but still, if I am given with a battery of unknown EMF, say E, what I can do is, you connect that battery along with the galvanometer, keep on moving this till you get the balancing line 0. Say this is L1. Now shall I write E is directly proportional to L1? Why, sir? Because if I had used 8 volt battery in the previous discussion, I should have gone to 8 meters. If I had used a 5 volt battery here, experimental cell, then I should have gone to 5 meter. If I had used only 1 volt battery, I should have gone to only 1 meter. That means EMF of a cell is directly proportional to the balancing line. Connect the unknown cell. Find out the balancing line. Take a known cell. You will have different cells of known EMF in the laboratory. Take them and connect it here. Say I have a battery of known cell E2. Connect it. Sir, balancing length has reduced to L2 or increased to L2, whatever it is. Suppose if I had taken a stronger cell than the experimental cell, balancing length would increase. If I had taken a weaker cell, balancing length would decrease. According to this cell E2, I'll get another balancing length. this is known, this is unknown, this is known, right? This is known battery which is taken from the lab, and this, you know this balancing length, you know this one. Divide them, because proportionality constant must be same for both. So what is E by E2 is equal to L1 by L2. Of course, in the laboratory you do E1 by E2 is equal to L1 by L2, and so which is unknown among them? This is the unknown, this is known, this is known. Can't you find out this? That is called comparison of EMF of two cells. E1 by E2 is equal to L1 by L2. First connect one cell of known value, find the balancing length, and another one unknown value, find the balancing length. Out of the 4 values, only one is unknown. You can find it out. This is the beauty of potentiometer, and potentiometer is used to determine the EMF of cells, and it is also used to determine the internal resistance of the cell also. Regarding internal resistance, you have theory in your book, you can look into that. Okay. Okay. Now, right. If you want that theory also, let us spend some 2 or 3 minutes regarding that theory also, because most of the people have forgotten that theory. How to find out the internal resistance. And before going to the internal resistance, you must know this theory. Whenever a battery is connected across a resistor like this, suppose this is EMF of the cell, whatever the voltage available across this cell, IR, this is not the EMF, because some voltage will be dropped across the internal resistance of the cell also. So this IR, I is the current in the circuit, this IR plus this IR, that together makes E, right? E is equal to IR plus I small r. Voltage drop here, voltage drop here. That is E. So full voltage is not available across this. So you know that I is equal to E by R plus R. Right? This formula you know it. Then what is the terminal potential difference? This one, V is equal to voltage available across the terminals of a cell. That is V equal to IR. I is E by R plus R. I R. I'll write it as R. This is the formula. Okay, we will do the same thing. So whenever a battery is EMF of the battery is measured with open circuit, you will get the EMF, right? If this is open, then no drop across this internal resistance, right? You will get the full EMF. As soon as some circuit is connected here, then there will be an internal drop, and you won't get the full EMF. You will get a terminal potential difference. This theory must be clear to you. Okay, now moving on to the potentiometer. Sir, I want to measure the internal resistance of a cell. What I will do, sir? What you have to do is, we do the experiment like this. Take the battery, of which internal resistance has to be calculated, connect it to a galvanometer, and measure the balancing point. So potentiometer is ready with a long wire, and primary cell is connected to the long wire, and potential divider arrangement is ready, and the primary cell will divide the voltage. Now connect this battery of EMF E, internal resistance R, across this. Okay. Now measure the balancing length. I will say the balancing length as say L1. Now remember, this battery is open. No current is flowing through this circuit. No internal drop. Full EMF appears across here, right? Now the EMF available across this, EMF voltage available across the battery is EMF. That EMF is balanced against L1 now. So shall I write EMF is directly proportional to L1? Full EMF of the battery is available because battery is not connected to anything. Now second time, what you have to do is, I'll rub all these things. This is not needed for me, so I will finish it here only. E is directly proportional to L1. Connect this battery against a resistor R. Connect this R now. When you connect this R, suddenly voltage here drops from EMF to some other value. Why, sir? This, out of this EMF, some voltage is available here. A small voltage is dropped across this because current starts flowing. Last time the full EMF of E was available because there was no drop here. Now current starts flowing, a small drop appears here across this. Suppose this is a 5 volt battery. Last time 5 volt was available. Now some current flows through this, so only 4.8 volt is available. 0.2 volt is dropped. And that V is terminal potential difference, that is this one. That is not EMF, that is less than EMF. That means now the total voltage has dropped here. Balancing length, this much is not needed now. Lesser balancing length is enough because the total voltage has decreased. So I call it as V now, terminal potential difference, because it is no longer E, because you have allowed the current to pass through the cell. So the EMF drops from E to V. V is proportional to L2. Now the balancing length little bit less is enough. What is V? V is ER, V equal to IR. This terminal potential difference is IR. I is E by R plus R. I is E by R plus R into R. So this EV is equal to IR. Is proportional to L2. Take this formula, take this formula. You will exactly get the same formula which you were using for practicals. Now divide these two. Can I divide these two? E is proportional to L1. ER by R plus R is proportional to L2. So E divided by ER divided by R plus R, left hand side, this by this, is equal to, so constant of proportionality gets cancelled, L1 by L2. Is it so? L1 by L2. What? E gets cancelled. E gets cancelled. So this goes to the numerator. R plus R by R is equal to L1 by L2. Okay, cross multiply it because we want the internal resistance here. One thing you can do, R by R, 1 plus R by R. R by R, R by R is equal to L1 by L2. So R by R is equal to L1 by L2 minus 1. Okay. What is R? R is equal to R into L2, L1 minus L2. Do you remember this formula? Internal resistance R is equal to L1 minus L2 by L2. Same formula. So, but know the theory behind this, right? This is what you are doing with the potentiometer. So it is used to find out the EMF of a cell and internal resistance of a cell. Now we will go on to the problem, right? Next problem on potentiometer. First problem on potentiometer. Yes, a potentiometer wire has a resistance of 20 ohm and length 10 meter. It is connected in series with a battery of EMF 2.5 volt, 2.5 volt and negligible internal resistance and an external resistance of 5 ohm. Fall of potential in millivolt per meter is, okay, this is not complete problem. They are asking you how much voltage is dropped per unit length of the wire, that's all. Read the problem, you need not write it because you have the PDF form of the question paper. Otherwise it takes a long time to write it. By the time you finish the problem, you will lose interest in the problem itself. A potentiometer wire has a resistance of 20 ohms. So I will read the problem. You just look into what we are going to write. A potentiometer wire has a resistance of 20 ohms. So long wire has a resistance of 20 ohm. And a length of 10 meter. Okay, 10 meter in length. Then it is connected in series with a battery of EMF 2.5 volt. Okay, battery of EMF 2.5 volt and negligible internal resistance. So no internal resistance. And an external resistance 5 ohm. This is another way of saying internal resistance, that's all. There is no internal resistance, but there is an external resistance. Why can't you take this as internal resistance itself? You can. Fall of potential in millivolt per meter. Millivolt per meter. What is this? Yeah. If you see here, there is a hurdle. You can't apply 2.5 volt. Completely do this 20 ohm. Not possible. Because there is 5 ohm waiting for it. First of all, find out what is the current in the circuit. So this is a wire. It has a resistance. It has a length. And these wires don't have a resistance. But here is one more resistance. What is I? I is equal to E by R plus R. What is E? 2.5. R plus R. R plus R can be written as 5 plus 20. 25 total, 5 plus 20, all of them are in series. So what is the current? This is 1 by 10 times 0.1 ampere. 0.1 ampere flows here. When 0.1 ampere flows here, we want the potential drop per unit length across the wire only across the wire. So if you want so, what is the voltage drop across the wire? Voltage across the wire is equal to I into resistance of the wire only. What is current? 0.1 ampere. resistance of the wire 20, that is 2 volt, right? So out of 2.5 volt, you see the beauty of these numbers. You need not work it out at all. You can go for shortcut. Now I can say how is the shortcut. 2.5 volt, divide it in the ratio because they are in the series, 20 and 5. How do you divide for 20 ohm and 5 ohm? Current is same, so V is equal to IR. How the resistances are, in the same way the voltage will be, directly proportional. So 2.5 volt, 2 volt here, 0.5 volt here, that's all. So 2 volt is here, and what is the potential drop per meter? This one as potential per minute length. Potential drop per unit length. If you want to calculate it, then it is 2.5 volt by per unit length 10 meter, 0.25 volt per meter. But they want it in millivolt per meter. How to get millivolt? If you want a milli here, multiply by 10 to the power minus 3. 0.25 into 10 to the power minus 3. I will divide by 10 to the power minus 3 also. But otherwise it will not be milli. So multiply and divide by. So volt per meter, correct? Okay, what is this? This I can take it as milli. So what is this one? 10 to the power minus 3. When it comes to the numerator, it becomes 10 to the power plus 3. That means 1000. This one. This is 1000. 1000 into 20, 0.25, 250. Then this, I want it milli volt per meter. 250 millivolt per meter. We have the answer? We don't have the answer. 5 ohm, 2.5. Oh, no. Here we have gone wrong. It is only this voltage you have to take. It is 2 volt. Okay. It is 2 volt across the wire. Potential drop per unit length is 2 volt across the wire, 0.2 volt per meter, 0.2 volt milli, right? And this is 200 millivolt per meter. Option is 3, third option. Going to the problem, it is 2 volt across the wire. That is the only thing you have to divide it across the wire. So option is the third option, 200 millivolt per meter. We'll go to the next one, next problem. Yes. Yes. A potentiometer wire of length 10 meter and resistance 30 ohm is connected in series with a battery of EMF 2.5 volt and internal resistance 5 ohm and an external resistance of R ohm. If the fall of the potential along the potentiometer wire is 50 microvolt per millimeter, then the value of R in ohm is. Okay. This is the reverse of this problem. Just now we have worked out. We will transfer the data to the problem. There is a potentiometer wire. There is a battery connected across the wire, and there is a resistance box also, right? There is a 5 ohm internal resistance and an external resistance. Okay, external resistance and internal resistance all are included. We need not bother. We can simply add all the resistances. A potentiometer wire of length 10 meter is connected to and having resistance 30 ohm. Okay, 30 ohm. Is connected in series with a battery of EMF 2.5 volt and internal resistance 5 ohm. Okay, here we have one more internal resistance. Is connected with an external resistance R. Okay. Then fall of potential along the potentiometer wire is 50 microvolt per millimeter. So across this wire, fall of potential is potential drop per. Okay, I'll write 50 microvolt per millimeter. Now I can write volt per meter because micro, milli, everything I have included, right? 50 microvolt per millimeter. Microvolt, everything is included. 50 microvolt per millimeter. So what is volt per meter? This is plus 3. 50 into 10 to the power minus 3. Minus 3 becomes plus 3. Plus 3 minus 6. Minus 3. Volt per meter. That is obtained. Okay. How much voltage is dropped across the wire per meter? We have got it. What is the total voltage drop across the wire? Can you find it out? This is voltage drop per meter. But this is 10 meter in length. So total, I will call this as phi. voltage drop per millimeter or per meter, I will call it as phi. Total voltage across wire. What is this? Because once I get the total voltage across the wire, I know the resistance. I can find out the current through the wire, because V equal to IR. If you know the voltage across any component and if you know the resistance, can't you find out current? V equal to IR. Once you get the current through the wire, that should be the current in the circuit. Then you can find out this R. So now you have to tap this wire. Just go on talking to the wire. It will tell you what is the current, because it is having so many data. So you can get the current from the wire. So total voltage across the wire is V across the wire is IR. What is I? Okay, IR means current into resistance, I into, okay, I will write I is, what is the I? Okay, that is, no, not from that formula. Voltage across the wire is, per meter is 15 to 10 to the power minus 3 volt. What is the voltage across the wire? Total, phi into length, right? Because per meter I have here. For this much meter, how much? Okay, 50 into 10 to the power minus 3, that is for 1 meter. For 10 meters, how much? So for 1 meter, this is the voltage. For 10 meter, how much? That is the total voltage across the wire. That is equal to, this is 10 to the power minus 2 totally, 0.5 volt. Now, what is the current in the circuit? Current through wire. Current through wire, I is equal to voltage across the wire, 0.5, and resistance of the wire, 30 ohm. That is equal to 5.1 za, 5.6 za. That is called 10 by 60 it is, right? Or 1 by 60. Multiply by and divide by 10. That, okay, let this be 1 by 60 amperes. I think I am going correct, right? Voltage drop is 50 microvolt per millimeter. Minus 3. 50 milli, okay, this is correct. Total voltage across the wire is 50 milli into that total length, 10. So this is minus 2, 0.5. Current through the wire is I is equal to V by R, only for the wire. V is 0.5 by length is, resistance is R by 30. So 0.5 is 1 by 60. Yes, this is half. I could have done it directly. 0.5 is half, 1 by 2, 1 by 60. Now the question is, what is I? What is R? Now for the whole circuit we will apply it. For the full circuit, I equal to E by R plus R. For full circuit, I is equal to E by R plus R. I is same because whatever current flows through one of the component in series, that is the same current flowing in the whole circuit. So 1 by 60 is equal to E. What is E? Where is E? 2.5. This one. Capital R plus R. R means all the R's. 30 plus R plus 5. 30 plus R plus 5. It is every R you have to include. 5 plus R plus 30. Now this is the only factor which is unknown. You can do that. So cross multiply it. 30 plus R plus 5 is equal to, of course, this is 35. Let it be 62 times 120. Then this is 150, right? Because 62 times 120, then half is 30, 120 plus 30 is 150, then 35 plus R is equal to 150, R is equal to 115 ohm. We have that option, fourth one. So that is the thing. So you should have a clear idea. First of all, find out the current through this wire only, find out the full voltage across the wire, then current through the wire only. That is the current in the circuit. I equal to E by R plus R will serve the purpose. So option fourth one, this option. Okay, we will move on to the next one. Yes, 85. When two cells of EMFs 1.8 volt and 1.2 volt are connected in conjunction. Conjunction means one after the other. That means in series. Balancing length on a potentiometer wire is 540. The balancing length when they are connected in opposition. Okay. When the two cells are connected in series, such that they send current in the same direction, that is conjunction. Opposition means they should send the current in the opposite direction, but both are in series. Okay, the circuit will be like this. Read the problem. When they are connected in conjunction, that means to send the current in the same direction, balancing length is 540. The balance length when they are connected in opposition is, okay, it is just a comparison of two cells in series. So this is the potentiometer wire, this is the battery to energize it, primary cell, and here we have two cells in series and the balancing length is 540. Okay, now shall I write E1 plus E2? So E1 plus E2 is proportional to 540. When they are connected in opposition, what do you mean by opposition? Connect this one in opposition like this, E1 minus E2, right? So E1 minus E2, the balancing length should decrease because the total EMF will be E1 minus E2 is proportional to what balancing length? Setup is same potentiometer, only those batteries are connected and they are connected in different ways, that's all. So what is the balance length? E1 plus E2. So I can write the value 1.8 plus 1.2 divided by, okay, E1 minus E2 is proportional to L E1 minus E2. 1.8 minus 1.2 is equal to 540 divided by L. This is 3.6. Am I right? Yes, that is equal to 540 by L. And this is 0.2. Bring this here, L here. L is equal to, this will be 810. Balancing length is 108 centimeters, correct? So this is 108 because 54 twos are 0.1, this 0 will consume this point. 54 twos are 108. So 108 centimeters. Option is third option. Yes, it is 108 centimeter. Very easy problem. Only you have to know what is conjunction, opposition and all. We will move on to the next one. Yes. A cell is balanced on 125 centimeter length of a potentiometer wire. Okay. When a cell is connected, it gets balanced for 125 centimeters. Then when a resistance of 2 ohm is connected across the cell, the balancing point is obtained at 100 centimeters. Internal resistance of the cell. Don't you think that it is the direct formula of finding the internal resistance, right? First one is L1, next one is L2. L1 minus L2 by L2 into capital R gives internal resistance, right? So we will list the values. I have explained the theory behind it. When the cell is balanced on 125 centimeter length of a potentiometer wire, initially there was no parallel resistance, right? So L1 is, and you do it for, we say that in the practical hours we say take infinity and find out the balance length. What do you mean by take infinity? Nothing is connected across the cell if you remove infinity, right? Now L1 is 125 centimeters. L2 is when the 2 ohm resistance is connected across the cell, the balancing length is 100 centimeters. And centimeters and all you need not worry because they get cancelled. And what is the extra resistance that you have connected across the cells? A cell, one of the cell, R is equal to 2 ohm. Now what is the internal resistance? It is the external resistance you have calculated into L2 divided by L1 minus L2. I think this formula is correct, right? L2 by L1 minus L2, capital R into, yes. This is what we have arrived at in the previous discussion. So what is this? Capital R into 100 divided by 25, right? Capital R, L2 by L1 minus L2, and yes, 2 into 100 divided by 25. I think I am not wrong, 100 by 25, so this is 4 times, and answer is 8 ohm. Somewhere we have, no, formula goes like this. So if you have a battery without any internal resistance, then E is proportional to L. Next, I bar means E by R plus R is L1. E by R plus R into R is proportional to L2. And if you divide this E by R plus R, okay, I'll divide it like this. E by R plus R is equal to, into R is equal to L1 by L2. Then, so R plus R by R is equal to L1 by L2. If I bring this 1 plus R by R is equal to L1 by L2, what you will finally arrive at? 1 minus, okay, R by R is equal to 1 minus L1 by L2. Yeah, it should be inverted formula, right? R is equal to R into, I don't remember the formula, this one always, L2 by L2. Yes, it should be inverted. Small r is equal to capital R into L1 minus L2 by L2. This is what you use, right? So what is the answer? L1 minus L2 by L2. R is 2, L1 minus L2 is 25 centimeters, by L2 is 100 centimeters, right? L2 is 100 after connecting the resistance, and L1 is 125 minus 100, 25, 4s it is 1 by 2, that is 0.5 ohm. So 0.5 ohm is the internal resistance. So our answer is first one. Go back to the problem. It is direct one, you can substitute. I don't remember, I don't spend memory in remembering this formula. So I can get it immediately. First option, this one. Okay, next problem. A potentiometer wire of length 1 meter and resistance 10 ohm are connected in series with a cell of EMF 2 volt and internal resistance 1 ohm and a resistance box including resistance R. All are connected in series. If the potential difference between the ends of the wire is 1 millivolt, the value of R is, right, potential difference between the ends of the wire. Which wire? A potentiometer wire of length 1 meter and resistance 10 ohm is connected in series with a cell of EMF 2 volt and internal resistance of 1 ohm. Yes, we can solve this problem. Read the problem. We will solve it. You should have a potentiometer wire. Better you draw a diagram here because so many data you cannot remember it so easily. So here is a potentiometer wire with a battery connected primary cell. A potentiometer wire of length 1 meter has a resistance of 10 ohm, okay, and it is connected in series with a cell of EMF 2 volt and internal resistance 1 ohm, okay, and a resistance box including a resistance R, okay, that is extra thing we have, okay, right. Then if the potential difference between the ends of the wire is 1 millivolt, this total voltage is 1 millivolt. This one. Voltage across the PD across the ends of the wire is 1 millivolt. Value of R is, yes. We have come across the same problem. It is a part of the previous problem, one of the previous problem. We know the voltage across this wire. We know the resistance of this wire. Can't you find out what is the current through this wire? Once you know the current through this wire, that should be the current in the circuit. You can apply I equal to E by R plus R. That is the only part. So, across the wire, I can apply across the wire V equal to IR. This is resistance of the wire, not this R. Okay, V 1 millivolt, I don't know, resistance of the wire 10 ohm. So what is voltage across the ends of the wire is 1 millivolt. It is correct. Resistance box, if the potential difference across is 1 millivolt. V is equal to I into R, it is a 10 ohm wire. So what is I is equal to this by 10 to the power minus 4 ampere. Now use this current as the circuit current itself. I is equal to E by R plus R. You can apply this. What is I? 10 to the power minus 4. That is I. And EMF. What is EMF? 2 volt divided by R plus R means complete external resistance plus internal resistance. 1 plus R plus and 10 ohm. Complete. 1 plus R plus 10. So what is the resistance R? So what I have to do now? I is equal to E by R plus R. Then, okay, I can bring this here. R plus 11 is equal to, this is 10 to the power minus 4 here. When it is coming to the numerator, 10 to the power plus 4. 10,000 into 2, 20,000. Remove 11 from 20,000. R is equal to, if you remove 10, 19,990. Now 19,990, 899, right? 19,900, 989, yes. Not 99, 89, 989. Because you have 11 here. If you had removed 10, it is 19,990, one less. This much ohm. That should be the resistance of the value of R, that is external resistance connector. So option B, second option. Yes. We will move to the next one. Yeah. In a potentiometer, for measuring the EMF of a cell, at null point, no current flows through. It is neither it's a main circuit, cell circuit. Cell circuit in the sense, it is the experimental cell. What do we connect externally, right? That one which energizes the that wire is the cell of the circuit itself. It is the main circuit cell because it is the primary cell. This is secondary cell, that is experimental cell. So no current flows through the experimental cell. You know, the galvanometer shows 0 reading. That is what we say. Balanced, that potentiometer is balanced means no current is shown by the galvanometer. Galvanometer is connected in series with the experimental cell. So no current flows to the experimental cell. And that is the speciality of this potentiometer. It doesn't draw any current from the cell. So experimental cell. So option is B. No current flows to the experimental cell. Whereas current because of the primary cell flows through the wire. That is true. Otherwise we don't get potential drop. So option B. We'll move on to the next one. Yes. Right. A potentiometer wire has a resistance of 20 ohm and length 10 meter. It is connected in series with a battery of EMF 2.5 volt and negligible internal resistance and an external resistance of 5 ohm. Fall of potential in millivolt per meter is very similar to the previous one of the problem. We will do it directly. A potentiometer wire has a resistance of 20 ohm. I can write 20 ohm here, and I should have a battery to energize it, that is called primary cell. And what else they are connected? Wire has a resistance of 20 ohm and length 10 meter, okay. And it is connected in series with a battery of EMF 2.5 volt and negligible internal resistance, okay, 0 ohm, and an external resistance 5 ohm. Find the potential in millivolt per meter. Did we do that once? I think we have completed that problem once. Fall of potential, we got 200 millivolt per meter. Okay, we will let us move on to the next question. It is 200 millivolt per meter. Yes, let us see the next question. The length of a wire of a potentiometer is 100 centimeter and the EMF of its standard cell is E, that is E volt. It is employed to measure the EMF of a battery. If the balancing point obtained at L equal to 30 centimeters from the positive end, EMF of the battery is very easy problem. Once it was asked for JEE level examination. Very easy question. Now, you should have a wire, the length of a wire of a potentiometer is 100 centimeter. Okay, I will write it here, 100 centimeter. And the EMF of the standard cell is E volt. So this is EMF, E volt. If it is employed to measure the EMF of a battery, okay. Now the balancing point obtained is at 30. So when I balance it against a cell of EMF, say E dash, I'll write. Then balancing length obtained is 30 centimeters. Their question is EMF of the batteries. Now one thing here is, of course no resistance here. One thing here is, suppose you want to balance a battery of EMF E itself. For example, suppose this is a 10 volt battery if you want to balance a 10 volt battery itself here, you need all the length, right? Because this 10 volt is distributed over the full length 100 centimeter. So can I take this as an experimental cell which is balanced against the full length of the wire? Yes, isn't it? So EMF E is distributed over the full length 100 centimeter. What about this E dash? E dash is distributed over 30 centimeters. What is E dash in terms of E? That is what the question is, right? Length of the potentiometer right is 100 centimeters. So full EMF is distributed over length 100. What EMF is distributed over 30? That's all you have to do. Divide this. E dash I will write first by E is equal to 30 by 100. So what is E dash is equal to? It is 30E divided by 100. Am I right? 30E by 100. And remember, you can't balance any this battery here which is greater than this EMF, because maximum available itself is this EMF. You can't balance any voltage source using voltage which is greater than this one. Similarly, so you can take this as 100. For this one it is 100. For what EMF? It is 30 centimeters. So this is answer. Option is third one, third option, 30E by 100. Okay, right, we will move on to the next one. A potentiometer wire has a length of 4 meter and resistance 8 ohm. The resistance that must be connected in series with the wire and an accumulator of EMF 2 volt, accumulator means battery, so as to get a potential gradient of 1 millivolt per centimeter on the wire is. See, this is one sample I have given which is asked for NEET 2015. We will do that now. You will get a confidence that such questions will be asked for the exam and I can do it. Right. What is the question now? A potentiometer wire has a length of 4 meter, okay, and its resistance is 8 ohm. Okay, potentiometer wire like this has a length of 8 meters, 4 meters, sorry, has a length of 4 meters and it has a resistance of 8 ohm. Okay, 8 ohm wire. It is connected to a battery series with a wire and an accumulator. Accumulator of EMF 2 volt and a wire means a resistor. In series with a wire and an accumulator of EMF 2 volt, no internal resistance, so as to get a potential gradient. Gradient means with respect to distance. Potential gradient of 1 millivolt per centimeter. So I'll write potential gradient is 1 millivolt per centimeter. If you move by 1 centimeter, then you will get 1 millivolt. How much voltage you will get if you move by 4 meter? That's what you have to find out. 1 millivolt per centimeter. Is it okay? That is equal to 1 millivolt per centimeter. Okay, that is equal to minus 2 becomes plus 2. 10 to the power minus 1 volt per meter. That means 0.1 volt per meter I get. What is the voltage across the full wire? Voltage across the full wire is, it is 4 meter in length. Multiply this 5 to that. 1 meter contains this much volt, right? 10 to the power minus 1 volt. What about 4 meter? So 5 into length. What is that? 10 to the power minus 1 into 4 meter. That is 0.4 volt per voltage, not per meter again, because per meter will be lost when you multiply it by length. We have multiplied it by length. So potential drop per meter is 10 to the power minus 1. What is the potential drop for 4 meters? 4 into 10 to the power minus 1. 0.4 volt is the voltage across the full wire. Now the question is, what is the resistance must be connected in series. What resistance must be connected in series in order to get this much of voltage? Now you know the voltage across the wire. Can't you find out the current through the wire? For wire only. So current through the wire is equal to voltage across the wire by resistance of the wire. What is the voltage across the wire? 0.4. Resistance of the wire 8 ohm. This is 0.1 by 2. That is 1 by 20 amperes. Multiply and divide by 10. Now this current itself is the circuit current. We have solved 2 or 3 problems of the same manner. Once you get the voltage across the wire, you can find out the current through the wire. That should be the current in the circuit. So shall I apply I is equal to E by R plus R? R plus R. I is 1 by 20 amperes. EMF of the cell accumulator, which is another name for cell, 2 volt divided by external resistance. All the external resistances R plus 8, R plus 8. Internal resistance is not given, but there is a wire resistance that also has to be considered. So what is the answer? 40 is equal to R plus 8, R is equal to 32 ohm. Do you have the answer? Yes, first option. That is 32 ohm. That is the answer. Option 1, right? This option, 32 ohm. So very easy problem. We have worked out of similar types. So you see, this is asked for recently in the NEET exam. You can refer some question papers. You can see at least one question from meter bridge or potentiometer. We will move on to the next one. Yeah, right. So we will go to voltmeter and ammeter later on in another class. So it's a very important part because I want to explain some basics regarding that. So for the time being, I will stop and see few more questions regarding this. This is the easiest part of the current electricity chapter, but very important. So you can score marks from this because one by one you have to start scoring. Scoring full marks in the entrance examination is not the way of studying. You have to go little by little forward because few marks itself will make your rank a very good one, right? So many days are left with, utilize it, revise all these problems, do well. Thank you. We will meet in the next class.